Hi everyone. Today we're gonna start chapter 8. Chapter 8 is about series and sequence. So let's first talk about sequence. Okay? Big idea. The limits of a sequence of real numbers can be determined in much the same way as that the limits of a function can be determined. Big skills, you should be able to find the limits of a sequence of real numbers given the general term. So here is the definition of a sequence. A sequence is an ordered list of numbers of the forms a1, a2, an, etc. Okay, it's also a function whose domain is a set of integers. Well, we know what a function is, right? Function, it could be like something like that. Let's say f of x is 1 over x. Okay, but if we restrict the domain to be natural numbers 1, 2, 3, 4, then what is a1? So a1 is like f of 1. That's 1 over 1 is 1. a2 is what? a2 is f of 2, which is 1 over 2, right? Then you can also see a3 is 1 over 3. a4 is 1 over 4. Okay? So you actually get a list of points. Okay? Alright, so that is sequence. A sequence may be generated by a recurrence relation of the form. So here's the formula of a sub n plus 1 equals to f of a sub n. Okay, so we express the n plus 1 term as a function of the nth term. So here these n, they are called the index. Okay, where a1 is given. Okay. A sequence may also be defined with an explicit formula for the nth term in the form of the nth term a sub n is a function of n, where n is a natural number. Let's look at some examples. Example 1. Use explicit formula to write the first 4 terms of each sequence. Okay, so let's see. We plug in 1. We get 1 over 2 to the 1 is 1 over 2, right? When we plug in 2, 1 over 2 squared is 1 over 4. And a sub 3 is 1 over 2 to the 3 is 1 over 8. a sub 4 is 1 over 2 to the 4 is 1 over 16. Okay, so given the explicit formula, and then to write the terms of the sequence is very easy. It's like just you plug in the x values in the function f, right? And let's look at part B. What is a1? Well, a1 minus 1 to the 1 is minus 1. And then n is 1, so minus 1 times 1 over n is 1, 1 squared is 1, plus 1. So the answer is minus 1/2. a2, we plug in n is 2, so minus 1 squared is 1, n is 2, 2 squared is 4, 4 plus 1 is 5. Okay, a3 minus 1 to the cube is negative 1, so negative 3 over 3 squared, 9 plus 1, so that's minus 3 over 10. a4 is minus 1 to the 4th is 1. So we have 4 over 4 squared, 16 plus 1. So 4 over 17. Okay, so you can see the terms. This is negative, this is positive, this is negative, this is positive. So you can see that the terms alternate the sign, plus minus plus or minus. So actually this is a alternating series. It's alternating sequence. Okay, and let's look at example 2. Use the recurrence relation to write the first 6 terms of each sequence. Okay, so we start with a1. And then to find A2, we plug in n is 1, right? A2 is 2, A1 plus 1. But A1 is 1. So we get 2 plus 1 is 3. What's A3? It's 2 times the previous term plus 1. So 2 times the previous term is 3 plus 1, which is 7. Okay, and then next, what is A4? Well, A4 is 2 times the previous term plus 1. So that is 7 plus 1, which is 15, right? And we can continue because we want to find 6 terms. A5 is 2 times A4 plus 1, which is 2 times 15 plus 1, that is 31. A6 is 2 times A5 plus 1. 2 times 31 plus 1 is 63. Okay, so those are the first 6 terms of the sequence. And let's continue. How about you pause the video here and try to work on this problem? Okay, are you done? All right, so we have A1 equals A2 equals 1. A3 is, we plug in n is 1, so A1 plus 1 plus 1 is 2. Okay, so actually the next term is the sum of the previous 2 terms. So A4 is then the sum of the previous 2 terms, which is 1 plus 2, which is 3. A5 is the sum of the previous 2 terms. So that's 2 and 3, we get 5. A6 is the sum of the previous 2 terms, and we get 3 plus 5, which is 8. Okay. So very easy, right? Given the explicit formula and then ask you to find the first few terms of the sequence, this is easy, okay? But next, we're going to do the opposite direction. So here is like we have 2 ways. It's either explicit formula where the a sub n is like a function of n, okay? Or we can have a recurrence relation where we see the relation between a sub n and a sub n plus 1, okay? So knowing this, and then we find the first couple terms of the sequence, okay? So this is easy because then you just plug in the n. But on the other hand, given the first couple terms of the sequence and ask you to find an explicit formula or a recurrence relation, this is usually harder, okay? And in our course, you're not required to I won't ask you questions like give you some first couple terms and ask you to find the formula. So we won't ask you this in this course. Our focus is about giving you the sequence, and we're going to ask whether the series converge or diverge. So we'll talk about series in the next session, okay? All right, so but here let's do more examples to help you to understand more about sequence. So I hope that you have heard sequence before, okay? All right, so let's look at this one. A n equals minus 2, 5, 12, and 19. Okay, let's find the pattern. Okay, usually first thing we try to find the pattern. Maybe you want to look at either the difference between two terms or the ratio between two terms to check. Okay, 5 and -2, the difference is 7. 12 and 5, the difference is also 7. 19 and 12, the difference is also 7. Okay, so that's why, wow, we can get A1. A1 is -2. A2 is 5. But what is 5? 5 is like -2 plus 7. That is how you get 5, right? What's A3? Well, A3 is 12. But what is 12? Can you find the pattern? That's -2 plus 7 plus 7. So you're adding 2 copies of 7. How about A4? 19. Yeah, but what is 19? Can you find the pattern? -2 plus how many copies of 7 do you add to it? 3. Okay, now let's see what is changing, what is fixed. Let's look at this. Okay, A4. 4 is changing, right? A1, A2, A3, A4. So it's like the index. -2. Did -2 change? No, we have -2 here, -2 here, -2 here, -2 here. So it fixed. How about the 7? It stayed there, right? But the 3 change. You see, this guy, A1 is like 7 times 0, and then you have like 7 times 1. That's why you can see it changed 0, 1, 2, 3. So the pattern, it changed. Okay, so now we can come up with a general formula. A sub n. Okay, let this index be n. Then we have -2, so it stayed the same, right? 7 stayed the same. But then this guy, it changed, so it's gonna be something about n. Think about it. If n is 4, what is 3? Well, 3 is 4 minus 1, right? So this guy should be n minus 1. See? This is a general formula of the sequence. Okay, so this is the explicit formula of the sequence. You can also write it as -2 plus distribute, you have 7n minus 7. So that is 7n minus 9. Okay? Yes, so we find the pattern and then what is changing and summarize it to get a general formula. All right, next. So next, my approach is I don't want to find difference. That's big. Okay, that's hard. Okay, I need to take the common denominator, but I want to find the ratio. Use the next term divided by the first term. Let's see, 4/10 over -3/8. Negative stays there. Okay, and oh, you can see the ratio is not quite good as well. Okay, so because it's not something we can cancel and get a nice ratio, so difference doesn't work, ratio doesn't work. Now let's see what are the terms. Okay, so can you notice that we have minus, plus, minus, plus, minus. If you see this pattern, the sign alternates. Your formula must contain a term -1 to the n or -1 to the n plus 1, depending on your index. Okay? And then, can you see the numerator? The numerator is 3, 4, 5, 6, 7. It's increasing, right? Yes. So it's changing. Okay, so let's try to write it down. Let me use black color. So A1 is -3/8. Okay? A2 is, I can think of, is -1 square. Because this is positive, it's like -1 square. And then we have 4/10. Okay? Can you see the denominator? What's the pattern of the denominator? 8, 10, 12, 14, 16, they're all even numbers, right? So because they are even numbers, so let's put out the 2. And this is minus 1 squared, 4, and 2 times 5. How about A3? Minus 1 cube. And then we have 5 over 12. 12 is 2 times 6. Have you realized the pattern now? Okay, so we have 1, 2, 3 that change. Okay, and we also have, like, this is like minus 1 to the 1. It changes, right? And the 3, 4, 5 also changes. The denominator 2 stay the same, but the 4, 5, 6 changes. Okay, now in general, A sub n. You see, if this is 3, this is 3. So, what do you guess? If this is n, then this is also n. Okay, how about if this is n? What's 5? What's the difference between 3 and 5? 5 is 3 plus 2. Then you can think about, oh, let's try this is n plus 2. Okay, so n plus 2 in the numerator. The denominator, 2. 2 is fixed. Stay there. 6. What is 6? Well, 6 is 2 times 3, or 6 could be 3 plus 3. But then which one? Do you want to put 2n, or you want to put n plus 3? Well, maybe we should look at the previous one. Let's look at 5. What's the relation between 2 and 5? Well, 5 is not 2 times 2, but 5 is 2 plus 3. Yeah, so we know the pattern is n plus 3. Okay, yes. And let's check our work because we check. We know A4 is what? 6 over 14. Is that equals to, we plug in, let's check whether this formula is correct. We plug in n equals 4. Minus 1 to the 4 is 1. And then 4 plus 2, do we get 6? Yeah. 2 times, what's 4 plus 3? 7. Yes, they are the same. It match. So this formula is correct. Okay. All right. So this is how, when I give you the explicit formula or recurrence relations, you can write down the first few terms of the sequence. Or if I give you the first few terms of the sequence, you can summarize and get the explicit formula or recurrence formula for it. Okay, but in our exams, I'm not going to ask you this. Our goal is like later in 8.3 and the remaining of the chapter is we talk about series. We want to know whether the series converges or diverges. Okay, all right. Then next, limits of a sequence. If the terms of a sequence approach a unit number L as n increases, then we say the limits a sub n equals to L exist, and the sequence converges to L. If the terms of the sequence do not approach a single number as n increases, the sequence has no limit. Then the sequence diverges. Okay, so the definition is very similar to limits of functions. You remember what is the limit of function? Well, we say limit x goes to infinity, f of x equals to L. What the picture is, you have L here. Your function is approaching to it, right? So here, same thing. If your sequence just like a list of dots, when it's approaching it, then we have a limit. Okay, so sequence is just like a special case of functions. So all the theorems hold for functions also holds here. Okay, so that's why we have the limit rules. So here are the limit rules we learned from Calculus 1 for limits of functions. And it's also true for sequence, okay? We have the constant, limit of constant is constant, limits of the sum or difference is the sum or difference of the limits of the sequence. And then for quotient, you gotta be careful. You gotta make sure the denominator is not 0. Oh, let me use different color to emphasize that. Okay, and constant multiple, you can put out the constant multiple C. And for products, limits of products is product of limits. And for the power, you can move the limits inside the power as well. So all the limit laws holds for calculus 1, also holds for sequence. Okay, here are more definition. A sequence is non-decreasing if the next term is greater or equal to the previous term. Well, if we look at the picture, non-decreasing means it could stay the same or increase, right? But you cannot decrease, so no. All right, so that's non-decreasing. How about non-increasing? Non-increasing means is either stay the same or decrease, right? That is non-increasing. A sequence is either non-increasing or non-decreasing, is said to be monotonic. Okay, monotonic. A sequence is bounded if the absolute value of the sequence is less than or equal to m for some fixed number m and for all of n. So, for example, if we draw the picture, okay, and let's say this is m, this is like minus m. Well, then the sequence has to be within this range. Okay, it must be lying in this range. Okay, so it must be lines in this range. Then the sequence is set bounded. Okay, and we also have the squeeze theorem or sandwich theorem. Okay, so you have three. Let's change a different color. So if you have three sequence, let's say okay, this is the one of the sequence, and then we have another sequence. Okay, this is the smallest lower sequence, and you have a sequence is bounded between them. Okay, let's do a different color, more obvious. Okay, so you have a sequence that's bounded between them. Then what happened? They have the same limits. Okay, so if the upper sequence and the lower sequence have the same limits, then the middle one must have the same limits. Okay, that is the squeeze theorem. And another theorem, I know you might be tired. Don't worry, after we cover the theorem, we will do tons of examples. Examples can help us to understand, okay? Just be patient for a few more minutes. Okay, so theorems. Limits of absolute value of a sub n equals to 0 if and only if limits of a sub n equal to 0. Okay, so what does that mean? You can think about an example. Okay, you can think about the let's say an is like 1 over n. This is a sequence, right? And you can see when n goes to infinity, like 1 over n will be 0. Okay, so then we know that limits of a sub n goes to 0. So when I ask you, how about minus 1 to the n of a sub n? This is minus 1 to the n of 1 over n. So this new sequence also satisfies that the limit when n goes to infinity is also 0. Okay? Alright, so that is the limit of sequence is 0 if and only if limits of the absolute value of the sequence equals to 0. Okay, and this theorem, you gotta be very, very careful. This theorem is only true for the zeros. Okay, in general, let's look at the remark. So in general, if the limit of the absolute value of a sub n equals to a number and that number is not 0, then the limit of sequence not necessarily equal to L. Think about this one. This example, if you look at the absolute value of that, it would be just 1. And 1, of course, the limits of 1 It's 1. It has the limits. But however, let's look at this sequence. This sequence is like minus 1, 1, minus 1, 1. Will it converge? It's just oscillating between minus 1 and 1, so it won't converge. The limit does not exist for this sequence. So this sequence, limit of when n goes to infinity of a sub m, actually diverges. So this theorem is only true for the zeros. Okay, for other number that is non-zero, it's not necessarily true. You have to be very, very careful. Okay, so one more theorem. A bounded monotonic sequence converges. Okay, what does that mean? Okay, a bounded monotonic sequence. So you remember what is bounded? Bounded means, okay, let's say this is the 0, and bounded means, let's say this is my n. Then the sequence lies in this range. Okay, monotonic means it's either non-decreasing or non-increasing. Please be careful. Non-decreasing and what's the difference between non-decreasing and increasing? So non-decreasing is not increasing. Okay, increasing means it has to strictly increase, so it goes up. But non-decreasing means it could be like stay the same or increase. So it's like, what's the difference between positive number and non-negative numbers? Okay, the feeling is like that. Positive number is positive, non-negative number, it could be 0 or positive. Okay, and as well, non-increasing is not the same as decreasing. Non-increasing, it could be decreasing or stay the same. It's like non-negative number, non-positive number, it could be negative or 0. Okay? So, a bounded monotonic sequence, monotonic is either non-increasing or non-decreasing. So, in terms of the picture, it's like this. So, this guy also converge. So, we know that if it's monotonic, it will eventually converge to some number L. Okay, this is what the theorem I'm going to talk about. All right, let's look at some examples. Yes. So we talk about the theorem. Now it's example time. I know all of you like examples. Okay, so example 4. Determine whether the following sequence converges or diverges. If it converges, find the limits. Okay, so let's look at this one. Part A. Wow, what does it look like? It's a rational function. Do you remember how to compute the limits of rational functions? We look at the dominant terms, right? What are the dominant terms? The dominant term of the numerator, so dominant term of the numerator is 2n cubed, okay? And dominant term of denominator is n cubed, right? Dominant term is the terms with the highest power. Okay, so after we figure out the dominant term, the limit of this rational function is just the limit of the ratio of the dominant term. Yes. Okay, and you see n cubed cancel, and we get 2. So this is our answer. Okay. And actually, this is a quick way of doing that. Just look at the dominant term. Actually, there is a formal proof. The formal proof is, in fact, what you do is you have the numerator and you have the denominator. Okay, you multiply by the top by 1 over n cubed and the bottom by 1 over n cubed. So you divide it by the highest powers. And then you distribute. So the first term, 2n cubed over n cubed is 2. And n over n cubed is 1 over n squared. Then we have 5 over n cubed. And then the bottom, n cubed over n cubed is 1. n squared over n cubed is 1 over n. Then we have 1 over n cubed. Okay, now when n goes to infinity, what happened? 1 over n squared goes to 0. 5 over n squared goes to 0. The bottom, 1 over n goes to 0. 1 over n cubed goes to 0. So you get 2 over 1. So this is a formal proof. But in the exam, you don't need to do the formal proof. You can just use this to show me. Okay? So, but you have to, okay? You have to tell me what is the dominant term of the numerator, what's the dominant term of the denominator, okay? Then you can use the limits of the ratio of the dominant terms. Okay, so everybody understand my requirement? Okay, if you have questions, feel free to email me or ask me during my online office hours. Okay, all right. Let's look at part B. Can you see the difference between part A and part B? They are almost the same, except part B has the extra factor minus 1 to the n. So then we're gonna use this theorem. Okay, we're gonna use this theorem. Okay, so let's see. Limit of n goes to infinity of absolute value of a sub n is, well, when you have the absolute value, the minus 1 to the n is gone. So you only have 2 x to the n cubed minus n plus 5 over n cubed plus n squared minus 1. All right. And this is exactly part 8. Part A, and we get that is what? 2. All right. Remember, if the limits of absolute value of a sub n is 2, can you tell what is the limit of a sub n? Okay, look at our theorem. When we have the limits of a sub n, absolute value of a sub n is 0, then we can tell the limits of a sub n is 0. But here, do we get 0? Do we get 0? No, this is not 0. So, but actually we know what a sub n is. A sub n is minus 1 to the n times this guy. So, a sub n behave like 2, at the end, it's not exactly equals to this sequence, but eventually it behaves like 2 minus 2, 2 minus 2, 2 minus 2. Okay, it's not exactly like that. It's behave like. It's like. Okay, all right. So when n goes to infinity, so you can see this guy is oscillating between two numbers. So the limit n goes to infinity of a sub n does not exist. So if the limit does not exist, what do we say? Okay, all right. Oops. Okay, if the limit of a sub n does not exist, we say the sequence diverges. Okay? All right. Okay, so let's continue to part B of the video.